introduction, good afternoon. My name is Yihan, and I'm a master's student in the System Software Research Group at Virginia Tech. Today, I will present our research on improving system performance through heterogeneous ISA designs. Specifically, our research look at cross-ISA execution of SIMD regions. So one of our motivations for this research comes from the increasing usage of heterogeneity in computer architecture landscape. Recently, we have seen chip designers embracing heterogeneous architecture in their product, from earlier ARM's Big Little, Intel Xeon Xeon Phi, to newer ARM Dynamic Q. However, existing commercial products offers no heterogeneity at ISA level. At best, some cores using this design supported extended instruction set, but at their base, all cores share the same ISA. Prior research shows that heterogeneity at ISA level can provide performance gain over single ISA heterogeneity. However, this was only done in an emulated setting. So we asked ourselves, can we actually embrace ISA heterogeneity using today's servers? But before we start spending a large amount of engineering effort to build such design, we want to make sure that leveraging ISA heterogeneity is actually promising in today's servers. So with this in mind, we first start searching for suitable servers that we can get our hands on, and we come across two servers with different ISAs. One x86-64 server, Xeon Gold 5118, that has 12 core and 24 two-way hyperthreading, and one ARMv8 server, the Cavium ThunderX, that has 96 core single-threaded. We selected benchmarks from 4 different HPC suites and run and calculated single-core, single-thread performance. Figure on the right shows the result of our study. As you can see, our ThunderX core are slower than its Xeon counterpart in every benchmark tested, but differs in degree of slowdown. The slowdown is not surprising, given that each Xeon core is clocked faster, and the ThunderX core have different microarchitecture design goals, trading off single-core performance for massive parallelism. What is interesting is that there are benchmarks that suffer a relatively low degree of slowdown, such as EP and K-means, and there is a 4-time difference in physical thread between these two servers. We believe it is possible to have potential performance benefit using ARM circuits in some scenarios. To test this theory, we performed another study. So this time, we selected 5 benchmarks from earlier test suite and run them with a variety of different composition ratio on the same servers. We measure the system's throughput, which we define as the number of benchmarks completed in a testing period, in this case 75 minutes. The figure shows the result of our new study. As you can see, neither Xeon nor ThunderX servers have a clear advantage in all tested scenarios. ThunderX servers perform better while the workload is mainly composed of low slowdown benchmarks such as EP and FT, whereas Xeon servers have higher throughput while there is an increasing number of relatively high slowdown benchmarks such as BT, LU, and Hydro. Thus, what we can draw from this result is that there is really no ISA that is good for all workload, which shows that the potential promise of using heterogeneous ISA designs for performance gains. So now we know that ISA heterogeneity can be potentially beneficial in existing servers. We went back to re-examine earlier benchmark slowdown result. We inspected 2 high slowdown benchmarks, Hydro from Livermore Loops and VPVTS from TSVC, and we found that both benchmarks contain a large portion of single instruction, multiple data instructions, which are also known as SIMD instructions. Surprisingly, latest ARM x86 server offer very different SIMD support. With the x86 server had a SIMD width of 512, and the ARMv8 server only had a SIMD width of 128. As SIMD instruction gaining more attention from chip designers as a means to extract additional parallelism in various application domains such as machine learning, computer vision, and cryptography, coupling together heterogeneous ISA servers that have significant difference in microarchitecture and SIMD extension provides an interesting platform for running diverse workload. So in this paper, we made the following contribution. We extended Popcore Linux compiler runtime framework to support a heterogeneous ISA design with cross-ISA SIMD migration capability. we analyze the effect of co-executing SIMD and non-SIMD workload on heterogeneous ISA system to understand the impact of ISA heterogeneity and SIMD and non-SIMD workload composition on system throughput. Lastly, we developed a migration wire scheduler that leverages new migration capability to improve system throughput. So our design effort contains 4 steps. First, we enable basic SIMD migration. After the SIMD migration is enabled, we want to ensure that migration is done correctly. And then we move on to optimize SIMD migration cost. And lastly, we use this new migration capability for performance gains. But before we begin explaining the details of our design, I want to clarify a few commonly used terms in our presentation. The first is SIMD region. SIMD region is a piece of code within a program that has SIMD instructions. Typical SIMD regions contain 4 abstract steps in a loop-style format, where you get the input index first, then you extract input elements based on this index, and you perform SIMD calculation, and you store SIMD result. Then, depending on the iteration, you either continue the SIMD loop or exit when you reach the boundary. So a SIMD region can vary in execution time. A program can contain any numbers of SIMD regions, and nested SIMD regions are considered as single SIMD region. And the second term is SIMD workload. SIMD workload is a set of applications in which each application has at least one SIMD region. So on the contrary, a non-SIMD workload is a set of applications that has no SIMD region. And a SIMD-intensive program is a program that spends more than 50% of its execution time in SIMD region cumulatively. So the first part of our design is to enable basic SIMD migration. The goal is to add at least one migration point inside each SIMD region. In the original framework, migration happened at equivalence point, and the function boundaries are one of naturally occurring equivalence point. So our solution is manually create equivalent point inside each SIMD region through dummy function calls and modify the compiler toolchain so that our modification get instrumented with migration check using as much as our original code as possible. And now you know how to enable migration. Where should we insert it? So the insertion location is determined at the beginning of each SIMD loop. The reason behind it is that generally at this point there is least amount of data that need to be migrated for the program to resume execution on the other ISA. So after we successfully created a migration point inside SIMD region, we must ensure that program executes correctly after every possible migration. Because each ISA can have different SIMD widths and the application can compile with different optimization configuration, the number of elements being processed in a single SIMD loop can vary. What we found out through testing is that correctness is not fully guaranteed after migration if no modification is done. So here's an example. Suppose we want to calculate 6 elements and we have 2 different ISAs. ISA A is capable of calculating 2 elements at a time, and ISA B is capable of calculating 4 SIMD elements at a time. So we start on ISA A, and then we get the index 0. We calculate the first 2 elements. We increase the index by 2, and we check if it reached the function SIMD region boundary or not. Because it didn't reach, we increase to the next iteration and the next. But now we just somehow decided we need to migrate to the other side. But this time, ISA B, who is capable of calculating 4 elements time, calculate 4 elements and create an index by 4. But what this results in is there's 2 incorrect calculations in the end, and this can cause unpredictable program behavior. So what we did is that we unrolled the SIMD code on both ISAs to the least common multiple of SIMD elements processed in the respective loops. So with correctness assured, we move on to optimize the SIMD migration cost. SIMD migration are meant to speed up computation, and in most cases, each SIMD loop iteration exercises relatively quickly. However, if compiler blindly insert migration point at the beginning of each SIMD loop iteration, as we discussed earlier, the program will suffer significant execution overhead. This overhead is mainly due to the additional system calls to check for migration decision. For SIMD-intensive program with large number of loop iterations that never actually migrate, naively executing system call to check at every loop iteration can harm performance. Nonetheless, applications should be responsive enough to migration requests to efficiently leverage heterogeneous ISA systems. So in order for the program to quickly respond to migration requests as well as incur low overhead, we propose a two-step profile-guided optimization approach that is inspired by the LVM's built-in profile-guided optimization to guide the insertion of migration point. So step one is profiling. So we instrument timestamp at entry and exit of SIMD regions and application itself. Then we compile and run the program, and we get an output file contains a timestamp each boundary. So step two is optimization. We first determine the desired responsiveness of the program, in which how often should we check for migration inside each SIMD region. And based on that, we eliminate instrumentation in a smaller region that does not meet this does not have the execution time longer than the requirement. Then for the remaining SIMD regions, which are bigger than the responsiveness interval, we instrument remaining SIMD region based on the determined granularity. And this way, we were able to reduce performance overhead to 5% on average. So lastly, we now have this capability of migrating SIMD regions inside the program. How should we use it for performance gains? So our solution is that we propose a SIMD-aware scheduler. The central scheduling idea of this scheduler is that the speed up gained from executing an application on the optimal ISA core should outweigh the slowdown other applications suffer from not running on the core. In short mathematical form, the speed up of incoming application divided by speed up existing app should greater than 1. So in order to do that, we had to further instrument our framework so that each application shall communicate to the scheduler at the program entry, exit, and after program migration. And scheduler uses slowdown information gathered from the profiling stage and real-time server usage to make additional scheduling decisions. And to reduce the complexity in decision-making, we categorize all applications into 3 slowdown groups: high, medium, and low. So to test our design, we propose the following experimental setup. We have 4 server configurations. Head dynamic is a heterogeneous system composed of 1 ThunderX server and 1 Xeon server with cross-ISA SIMD migration enabled using the aforementioned technique. Head static follows same setup but without migration capability. We also have 2 homogeneous setups. x86 is composed of 2 Xeon servers, and ARM static is composed of 2 ThunderX servers. All 3 static setups are considered as baselines, and applications for these baselines are compiled without migration instrumentation. Our experiment length is 75 minutes per run in order to limit as much as noise possible. And our evaluation parameter is system throughput. Again, is defined as number of benchmarks completed in a given interval. And for all 4 server configurations, the workload, we have the same workload generation script. Our workload generation script is trying to mimic a dynamic workload scenario. We have a predefined SIMD non-SIMD benchmark composition, and in the first iteration, we assign benchmark based on affinity, if possible, until all cores are occupied. And then we randomly assign benchmark from the remaining workload when cores free up, and we regenerate workload with the same ratio if the current workload is empty. We also have 2 testing scenarios, 2 benchmark case and a multi-benchmark case. The goal of in the 2 benchmark case, the entire workload consists of 2 benchmarks, 1 SIMD and 1 non-SIMD. The goal of this experiment is to determine the workload that yields the throughput gain for head dynamic case. By focusing only on 2 applications, we can carefully control individual benchmarks with different slowdowns. And using the insight we gained from this experiment, our second experiment considers a more realistic workload consists of multiple non-SIMD and SIMD benchmarks. So due to time restraint, I will only show 1 result from each testing scenario. In both scenarios, the number of SIMD benchmark is set to 1/8 of the entire workload. As you can see, in this case, our head dynamic case is able to have performance gain in both EP, K-mean, and FT with best of 36%. But as we move on to benchmark containing that has larger benchmark slowdown, you see that our head dynamic case started getting beaten by the x86 case because the benchmark suffers more from affinity. And we also have on average, 6% of non-SIMD benchmark migrate to ARM in order to yield x86 cores for benchmark with higher affinity to it. And we also found the conclusion that our head dynamic case always outperforms the head static case without migration. So moving on to the multi-workload scenario with the same percentage of SIMD workload, we actually have our design actually outperform every single baseline with average performance gain of 14.6% with best of 26%. And on average, 23% of total benchmarks migrate to ARM in order to yield some application that has a higher affinity to x86. And on average, 24.7% of total migrate back to x86 eventually. So in conclusion, in the space of SIMD, heterogeneous ISA system can be leveraged for performance gain, and efficiently using ISA affinity and dynamically migrating application to use ISA optimal cores in heterogeneous ISA system can result in significant performance gain over homogeneous systems. And the fact that our design allowed two servers that almost 5 years apart in production to outperform two 2018 released x86 server is a strong validation of our result. And in short, no one ISA architecture fits all workload. Thank you.
Thank you, Yihan. So we have 3 minutes for questions.
A question that rises immediately, I think, is where are GPUs, for example?
So the thing is that we are
especially for SIMD.
Yes. So we are our design explorer is two CPU with two general purpose CPUs, so that they're capable of doing.
I understand. If let's say you wanted to add GPU,
Yes.
could you do fundamentally the same thing that you did, or would it be a dramatic change? Not the results, the what you need to do.
I think I think there will be changes need to be made, but not by that much.
So perhaps one very short comment. We have done something very similar in 2011. It's a little bit ago for 2012, where we have moved between GPUs and CPUs, and we have not compared CPUs with each other. So in principle, I think the workflow was not so different from what Yihan has presented. Of course, the means within the workflow were completely different. So it's possible. So further questions? Yes.
So in the performance graph that you showed, what's, I don't know, the ratio between the SIMD and not SIMD load?
So like in both cases, in the entire workload, SIMD accounts 1/8 of the time.
1/8. Okay.
Further question? So then I would have another question, Yihan.
Okay.
So have you thought about also optimizing the scheduler who is putting the work to the ARM and the x86 processors, so that this is not done dynamically but based on affinities, how you presented it, so that you put more intelligence into the scheduler?
Well, we want to. The thing that we want to, yes, you can put more intelligence into the scheduler, but you have to also think that you want to be very responsive. If you have too complex decision of making algorithm, that your system will not be responsive enough to making decisions, so that you might have more benchmark clustered on one server just waiting for migration decision to come back. So that's why we're trying to reduce the complexity by making it into 3 different groups, so that the decision making is faster.
Okay, thank you very much.